Hello and welcome to the Zero to ASIC course YouTube channel. Today I'm doing another interview and today it's with Thomas Parry. So hello Thomas Parry, how are you doing?
Hello, I'm good. How about yourself?
Yeah, I'm fine, thanks. So you're from Scotland?
Yeah, originally from Scotland, now living in Rotterdam in the Netherlands.
Yeah. And I got in touch because I saw, well, to be honest, it was the layout files for the GDS, for the shuttle that you did.
Mm-hmm.
Can you tell us the name of the project that you submitted?
Yeah, so it's the AMSAT, I think TXRX IC, possibly. I don't know exactly off memory. But yeah, yep.
It's a amateur satellite transceiver.
Yep, exactly. That's the plan. So the plan
Okay.
is to build up an amateur radio transceiver over the coming shuttles.
It seems to me like quite an advanced topic, or at least quite a difficult one.
Yeah, I wanted something that would be challenging. So
Yeah.
definitely something I can get my teeth into over a number of shuttles.
Yeah. So give us a little bit of info about your background, because we've only just met. I checked out your LinkedIn profile. It seems like you do this kind of stuff. So maybe you can just tell us how you got into the idea of the satellite transceiver, and also a bit of your background on previous ASIC experience or previous analog design experience.
Yep. So I started my career in the space industry in Scotland, designing basically power and RF systems for satellites. So that was really fun. But after a few years, I wanted to learn more about the IC level stuff. So when I moved country, it was a good time to also make that jump. So for the past maybe 2.5, 3 years, I've been working for a small design house called Systematic Design in Delft. And they're basically, I think, about 15 people, which are specialists in IC design, mostly analog design for sensors and power. So yeah, I'm not a complete noob to ICs, but neither am I a complete industry veteran. So about few tape outs over the past couple of years. It's about my experience level.
Okay. And how did you do the design? Well, I looked through the repo, and I'll link that in the YouTube. So you've got kind of two repos: the one that you submit, the Caravel one, but then there's quite an interesting one that seems like it contains all the design files.
Yeah, so that's really where I started. That's the kind of the main repository where I work in, and then obviously for Caravel, there's a different arrangement of files because it's the Caravel harness itself. So basically spun that off and put the different design files that taped out on the first submission into that. But mostly day to day, I work in the other repository. That's where I kind of build up the designs.
And that was, it looked like mostly stuff for Xscheme or Xscheme, or how do you pronounce that?
I say X scheme, but there's
Xscheme.
no promise that's the truth. But
Yeah.
yeah.
And Python and Matplotlib and stuff like this.
Yeah. So I use Xscheme for schematics, and then ngSpice for simulation, and then Klayout for the layout. But so yeah, that mostly works. But there's a lot of kind of processing stuff that's missing. You might get from a more commercial tool. So I tend to use Python to plug that gap for plotting and analyzing data.
Okay, so for your day job, are you using different tools then?
Yeah. So my day job main tool we use is the Cadence Virtuoso tool. Also sometimes MentorGraphics, Tana tools. So that's the kind of the industry standard tools. So it's good to have an idea of where they are, have an idea of what to expect, and then they're not that far. The functionality, you just have to plug some bits in yourself.
It's really interesting to talk to somebody who's actually got some ASIC experience. Because a lot of, like myself and a lot of people that I've been talking to, it's our first time. So we don't really know. And like someone like me, I've never had access to the kind of the industry standard tools. So I don't kind of know what the differences are. So it's interesting to talk to somebody who's actually using both.
Yeah, I think a lot of it comes down to risk at the end of the day. A lot of the expensive tools, especially the physical tools, people pay a lot of money to know that it's going to work and it's going to create reliable designs. Whereas with open source tools, there's not that promise. There's no one to shout at. So that's kind of one of the big differences.
And what happens if something goes wrong and you shout at one of the big vendors?
Well, I think how big it depends how big your company is. So for us, I'm not sure, but I'm sure if you're Qualcomm, then you can get Cadence this year pretty quickly.
Yeah, maybe not for a 15-strong design team.
Yeah.
Yeah. Has that ever happened to you?
No, I don't think I've ever had any issues with the tools. They're pretty mature now these days. We tend to work on more mature nodes, so 180, 130 nanometers, because that's good for analog design. So it's not
and cheaper as well, I guess.
Yeah, exactly. Yeah, so it's really easier to iterate and get a product out fast.
Yeah. Okay. So I've seen a little bit of the analog process by talking to Lakshmi. We did an interview with her about the PLL, and also Diego, who's doing an op-amp. So they kind of do some modeling with Xscheme, and then they do a layout in Magic or Klayout. They extract and then simulate and then kind of compare how close the extraction is to the thing that they simulated in the first place that they're trying to get to.
Yeah.
And then if it's not quite close enough, if it doesn't fit their specification, then they start tweaking things and changing things. Is that kind of like your experience, your process as well?
Yeah. Although it depends on the circuit. So, for example, the Bandgap circuit I did, that's a DC circuit. So the parasitics really aren't that important. Everything's so low frequency that extra capacitance is only going to really help you mostly. Whereas if you're doing something in RF, then extra capacitance and parasitics is going to really hurt your design. So it does depend on which circuit you're actually designing and laying out, what approach you need to take. So I mean, for some of the millimeter wave stuff that people are doing in industry now, they'll do full EM simulations on their designs. So that's a kind of a step above the parasitic extraction.
Okay. And one other thing that's I've not heard that's a bit different is that you're using Klayout for the layout.
Yeah.
And I think everyone that I've spoken to so far has used. If it's digital, then OpenLANE does everything for you. But because you're doing analog stuff, I'm assuming you're not really using OpenLANE much. You're just using the padring, as it were, and putting your analog design in there.
Yeah, I did use OpenLANE for a very small bit of digital.
Oh yeah, actually, I did see a little bit of small digital in there. Yeah.
But
I've not seen anyone do layout in Klayout. So can you tell us kind of what, like, my experiences with Magic? What's it like doing layout in Klayout?
And the main reason I did it was because it feels much more like the industry tools. So I'm sure Magic is nice to use, but I don't want to train myself in one way and then have to use a different tool during the day and always have that context switching. Whereas Klayout feels a lot like the Cadence tools, so I don't have to mentally shift in my mind. That's the main reason I chose Klayout.
Yeah, I've got to be honest here. I was probably 2 or 3 months into learning how to use other tools, and I thought Klayout was just a viewer because I'd never switched it into edit mode.
Yeah, no, I know it's weird. I think they should change that. They should make it so it starts in edit mode.
Starts up in layout mode, or make it more obvious.
Yeah.
But I suppose that's the kind of thing that you don't realize until afterwards. Okay. So can you do circuit extraction with Klayout as well then?
I don't think so. Yeah, there's certainly nothing.
So you have to use Magic to do that, do you?
Yeah.
So you're doing the layout in Klayout, then you load it up in Magic, do the extract. I guess you can just use tickle scripts for that. You don't even need to.
Yeah. So basically, I've got a flow now where just a bash script that I just type in the name of the cell that I want to extract, and it will start Magic, import Klayout, do the extraction, and then spit out the spice file.
Yeah, actually, I was quite impressed when I checked your repository out because you had these 5 kind of steps on like generate the design here, run the DRC here, run the LVS here, and they're all done just as a simple shell script. It's really nice to see that in the documentation because for someone like me that's coming to a project cold, I can just be like, all right, there's the shell script, look at that, see the commands, then see what is actually going on behind the scenes that does the work. And that's really cool.
Yeah, definitely. I think there's a lot more improvements to be made in documentation, but at least for the bash script, it's kind of self-documenting. And it means you don't have to type the same thing 1,000 times when you're really in the depth of the design work.
Do you have a kind of overall schematic of the thing that you've been making?
Not really. So in the Caravel submission, there's an overall schematic, I think, of the 2 different sections. So there's a Bandgap section and a phase lock loop section. So there's an overall schematic of each of those. but not of the overall system. That will probably start to emerge sooner, basically. Yeah, maybe in the next strata I'll have a half a system as a whole unit. Yeah.
Okay, so maybe you could give us because my radio understanding is pretty limited. So maybe you could give us like an overview of what is required for a satellite transceiver in terms of the analog blocks, and then kind of tell us where you're up to in terms of completing each of those blocks.
Yep. So for transmitter, which is my current phase, you need a digital analog converter to take some digital data, convert it to analog. And then you need a mixer to basically convert that baseband. So basically DC to whatever the bandwidth of the modulation is, up to some higher frequency. So you use a mixer to do that, which is fed by some form of a local oscillator, so an oscillator. And then in the simplest form, that's kind of it. You've got your baseband up to RF, and then you can basically get that off the chip with some kind of buffer. But what I'll be doing is basically going from baseband to an IF, and then another up conversion stage to the final RF to get that off the chip. So in that, you basically need the kind of more analog components of the digital analog converter, and then the more RF components of the mixer, the oscillators, and then you need something to bias that, which is the way the bandgap comes from. So everything is derived from on-chip currents. So you need some way of generating that current reliably. And then for the receive side, everything's basically the same, but backwards with different considerations.
And so you've got I'm just trying to, I'll put a picture of this up on the video when I edit it. So I'm remembering actually I might load up Klayout now so that I can ask you about the different sections, because they're, very, very interesting to look at, much more interesting than seeing the output of, I mean, when I first got started, it was super interesting to see all the standard cells and but then, as soon as you've got a project big enough, it's just like a big mess of cells and there's no understanding it. But then when I was kind of going through your design in Klayout, it was like all these intricate blocks with like repeated patterns and very, very cool look to it.
Yeah, you can start to see the function just by eye rather than
One thing I notice is, like on my submission, there was this grid of the power distribution network on layers 4 and 5, and in comparison, your design looks so clean. You've got like a block on the left, a block on the right, and then some wires that connect it all together, all perfectly evenly spaced, and then nothing else. So maybe we can just start from the bottom. So we've got this kind of fan out of. I guess what is that? Is that logic, using the logic analyzer to control it, or wishbone, or?
Yeah, so basically there's a number of control signals that I'm using the logic analyzer to control. So these are kind of static signals to change configurations. So that's basically coming from the onboard RISC processor.
Okay, and then we follow that up onto the left-hand side. We get to like a block of something from OpenLANE, some digital logic.
So that's basically what I've made is on that side, left-hand side, is a phase lock loop. And then I've made the digital portion of a fractional N divider, basically described it in Verilog, and then synthesized and placed and routed it. So it's basically a noise shaping type function that allows you to make a non-integer multiples of your reference frequency. It's like a sigma delta converter, where you can basically make fine steps over an averaged period of time with only having a small amount of quantized steps.
You keep a track of how long it's been on and off for and make sure you're switching states fast enough.
Yep, exactly.
Okay. And then below that, we've got a very regular block of 1, 2, 3, 4, 5, 6, 7, 8, 9. What number is this? 9 by 1, 2, 3, 4, 5, 6, 7, 8, 9 as well. 9 by 9 of something.
So I think that's probably the charge pump output.
Okay.
So basically, in the phase lock loop, to close the loop, you put out a current into a capacitor, and there's just a So it's basically just a current sink and source. Because I'm doing that off chip, I need to be able to put a bit more current than you normally see on chip. So that's why there's an array basically of the output.
And quite chunky traces as well.
Yep. Yep.
Yeah. Okay. And then above that, we've got another kind of then we've got the VCO. So this is actually, so on my Discord channel, we were talking about this, and one of the questions was, do VCOs normally look like decorative bathroom tiles?
Yeah, well, I think they always have quite a cool look to them, because you basically want to be careful about parasitics. That's kind of why there's a lot of
keep everything even.
Everything even, yeah, and also
so that's why you see symmetry.
Yeah, exactly. So it's basically 4 elements. So it's a ring oscillator. So there's 4 basically inverting amplifiers that feed around each other like a snake eating its own tail, and then that's basically how the oscillation works.
And then how do you tune the frequency of that?
So in the amplifiers, there's basically a PMOS load that you can change the gate voltage, and from that you change the amount of current that's inserted into the amplifier, which basically makes it faster or slower.
Okay. Yeah, it looks really cool. So you drew this all by hand in Klayout, or did you script it?
So basically, for the individual components, like the MOSFETs, I used the generator in Magic, and then exported out of Magic into Klayout.
Okay.
And then, yeah, from then on, basically arranged by hand.
Yeah, it's really nice. It looks like a bathroom tile. And then we've got like a couple of kind of big regular blocks of 1, 2, 3, 4, 5, 6, 7, 8 by 8 by 4, and then there's 2 of them together.
Yeah, so they're the output drivers.
So it's for a large current output drive.
Yeah, theoretically it can get a 0 dBm differential RF signal off chip. That probably won't happen, but theoretically.
Yeah. So part of the PLL is off chip, did you say, or part of the transceiver?
Part of the PLL is off chip, yeah. So basically you need to have a compensation filter to close the loop.
Okay. And you can't do that inside the chip, or it's too dangerous. You want to be able to adjust it.
You can do it inside the chip, but you need to be able to know quite a lot about the stability characteristics of the system, because it would be safer just to do it off chip, and then I can basically change capacitors and resistors as I need.
Okay. And by doing that, do you also lose a bit of performance because you're having to go back out of the chip and then through a filter and then back into the chip, or does it not really make much of a difference?
Well, I think the biggest performance hit will be power, because you have to drive more current off chip and area. But for a design like this, that doesn't really matter. It's just for research, I guess you can say.
Okay. Yeah, it's going to be really interesting to see the performance of this. I guess you're quite excited about knowing that.
Yeah, definitely.
In fact, that's a question that I didn't come up with, but is interesting to ask, is how are you going to characterize the design when you get it back? Do you have like access to all these kinds of expensive tools in your day job? So
in my day job, I have access to a thermal chamber, which will be useful for the Bandgap reference, because I can measure its behavior across temperature. And also I've allowed the ability to measure the individual components, so the bipolars and the resistors separately, so we can actually characterize that and compare it against the models. So hopefully the community can use that for further designs. In the PLL, I don't have a lot of that equipment myself, but I have access to amateur radio projects basically that have remote labs that I can send the chip to, and then they'll hook it up to the equipment to measure it, and I can access that over the internet. So,
oh, that's cool.
Yeah, so they're quite useful.
Okay. So then if we take a look at the right-hand side, we've got kind of 3 blocks that look pretty similar to each other, except the top block's got an extra section.
Yeah, so those are basically the Bandgap reference. So there's the same core is replicated, I think, 3 or 4 times. And then there's a trimming circuit, which is on some of them. And then I think there's another one where I can access the voltages rather than the currents. It's basically the same design, but permeated in different ways to be able to measure it differently.
Okay. So that's part of the what you were just talking about with being able to characterize it afterwards.
Yeah, exactly.
To get access to the different measurements you need.
Yeah.
Okay, yeah. I love the incredible spacing in the routing. So like one of the I'm trying to put together lots of different people's projects onto one chip to maximize space usage. And I've got kind of 16 different designs in there. And for my tests, I'm just using the same design 16 times. So really what I want the tools to do is kind of make a nice even bus that snakes through everything and just connects the pins, and they're all in the same order and it looks perfectly laid out. I want it to look like this, but it looks like a complete mess instead with still short circuits and things like that.
Okay, yeah. I mean, that's the thing, layout is where you get to practice your OCD tendencies and make everything perfectly
Absolutely
arranged.
perfect. Yeah. So did you draw this by hand, or was this scripted?
I'm drawn by hand, yeah.
Okay.
So
so I've looked a little bit at the scripting in Klayout, and that seems like it's quite a powerful thing because you've got a Ruby and a Python kind of interface to it.
Yeah.
Is that something you've looked into at all?
Yeah, so originally I replicated the component generation in Python in Klayout, but in the end I dropped that because things were getting updated and I wasn't maintaining it fast enough. And then I also made a VA generator in there. So I have used that, but it's quite powerful. I'm definitely interested to see what can be used for in the future.
Yeah. Yeah, I know that the Efabless team are working to kind of integrate Klayout a bit more tightly into the OpenLANE tools. For example, in the first shuttle, if you had problems, you would often get just like lists of locations, and that file was essentially useless. I mean, you could type those numbers in, or you could pre-process it with Python, spit it out into something else that you could then import into either Magic or Klayout. But now they're actually generating XML files that you can open directly with Klayout, and it will highlight all the types of errors, and you can just click around and see where they all are, which is much better.
Yeah, definitely. So during the first submission, I had some minor issues with DRC when checked by Calibre. So I actually worked quite closely with the team, and they shared some very useful Klayout tools there to do DRC check in Klayout, which was very useful in the end. Yeah.
Okay. So now might be a good time to do the little break that I've started to do in the middle of these videos, where I ask my lovely guests to pick something from the terminology page of the website. And you chose something that I didn't have, which is called corner.
Yeah, so corner is basically the way that you describe different manufacturing offsets, or variability is the best way of saying it. I think originally it comes from the fact that you can have you have your PMOS and your NMOS, and they can be fast or slow, which basically is how much gain or how fast the device is. So if you imagine a quadrant where you have a fast, slow, slow, fast, slow, and slow, fast, and these basically are simulation models provided by the foundry with the same devices but at different different performance levels. So you get spread across. It's meant to be realistic to what you get across many different wafers. So yeah, that's very important for analog design, that you need to make sure that design works across all corners, and then you can include temperature and voltage in that as well. And sometimes that can be challenging to get the thing working across all corners. So just getting it working in the first place in a typical is really just the start of the work.
TT. Now it makes sense. Yeah, TT. So I've done a little bit of work with simulation and loading the Spice libraries. And one thing that I do is delete all the corners and just use TT, because it's much faster for ngSpice to load up.
Yeah, definitely.
So, but when you're doing a design like this, you need to make sure that the simulation that you're getting out from ngSpice matches your specifications across all those combinations of slow and fast MOSFETs.
Yeah, so I mean, for a Skywater project, you maybe don't have to do that because you don't care so much about the yield of the chip across many thousands or hundreds of thousands of units. But it's still useful to get an idea of how sensitive your design is to small variations. So if you run it through different corners and see it still works, it's quite a high likelihood it's going to work in real life.
Great. That's a good one to a spot that I'm missing. So thanks for pointing that out.
Yeah,
I'll get that page added. Okay. So back to the transceiver. Another question I've got for you is how are you going to get the RF signals in and out?
Yeah.
Can you use the padring, or do you have to somehow jump over those I/O blocks?
Yeah, so don't really have a good answer for that one. My answer really is I made a buffer to try and get as much power into the device or into the I/O cell as possible. And it's basically, it's a signal integrity nightmare going through there. So I'm just going to try and get a sensitive receiver and hopefully pick up. So I should still get some signal. It's not going to be power, but it's going to be enough signal to do some measurements. So there was an option to expose pads for external wafer probe, but I don't have access to one. And on the balance of trying to track that down, I felt my time would be better just moving forward. So yeah.
It will be interesting to find out anyway.
Yeah. Didn't really have any other option, so we'll see. Should be able to get enough signal off to get a measurement, but it's not going to be perfect, that's for sure.
Yeah, maybe because of the type of package. I'm going to get this wrong. It's wafer level chip scale package.
Yeah, I think that's right.
WLCSP. Yeah. Okay, yes. I always get like those 5 in some different order. Would there be a possibility to kind of put, because you're very close to the silicon on these packages. So like, would it be possible to kind of make a new bond pad that you somehow get access to?
Yeah, I mean, I think some people are planning to get the bare dies and probe it externally. But I think it's not so much the package the problem. The package is actually potentially very good for signal integrity. Mm-hmm. It's just that the I/O cells are digital GPIO I/O cells. So hopefully in the future we have the opportunity to go straight to the pad without I/O cells in the way, and then more things are possible. So fingers crossed there.
The first 8 pins on the MPRG-IO of the Caravel, aren't they analog switchable pins?
Yeah, they are, but for low frequency signals, that's not a problem, or low power, because it doesn't matter. Anything high power or high frequency, the routing is far from ideal, essentially.
Okay, so potentially a silly question here is it kind of with a transceiver? So for the receiver, that's going to be low power, but for the transmitter, do you sometimes have like the amplifiers on the chip, on the die as well, and so you don't need an external amplifier?
Yeah, I mean, it depends how much power you want to get out. So you're probably not going to get you're definitely not going to get a 10-watt RF power amplifier on there, but maybe half.
10 watts goes a long way.
Yeah, so I mean, if you think about how much power a Wi-Fi device puts out, and they do those on die at the moment. So
okay, yeah. They're kind of milliwatts, aren't they?
Yeah. So I think maybe even 100 milliwatts. But
okay,
RF power amplifier design is definitely an interesting spot. It's a challenging place to be working. So hopefully have a look at that later on in the project, but I'll leave that the stretch goal.
I like it, the stretch goal. So that kind of takes us on to the next topic, which is what's the next steps then?
Yes, the next step is basically to try and complete the transmit chain. So I've got the Bandgap reference now to divide and set everything. I have the A phase lock loop. So in the first shuttle, I didn't do anything with inductors because, I just basically closed that door and decided to progress without inductors. I've done a lot of work recently trying to design on-chip inductors, which should make the performance in the next chips much better. So a higher frequency oscillator using an LC oscillator topology, the 8 gigahertz is the first thing that's going to go on there, and then a DAC. And hopefully get the full transmitter chain in the next submission as a plan.
Amazing.
Yeah.
Yeah, it's really, really cool to see this kind of stuff being done.
Yeah, I think it will be an amazing feeling to actually talk to a satellite with an IC you designed yourself, all open source. So yeah, that's the hope.
And could you put another one on the satellite so you have a matched pair?
Yeah, if anyone's got a satellite, I'll put it on there.
Awesome. Yeah, something to look forward to.
Yep.
Okay, so maybe this can be our last question. My experience and most people's experience of the open source ASIC tools and the shuttle opportunity has been kind of firmly in the digital domain. And so, but there's quite a lot of interest to kind of have a play with the analog stuff, but it seems like another world. So could you tell us, it seems from listening to you that the tool's in a completely usable state and the PDK is like completely usable for this kind of stuff.
Yep.
Is there something that is missing that would make it a lot easier? Or how does it compare to kind of the PDKs that you're used to?
I mean, at the core of the PDK, there's not actually that much difference. So the model, it's a BSIM model for the MOSFETs, and that's what you're using commercial PDKs. I mean, the core of it, everything that you need is there. It's just you just have to put the pieces together. So maybe the harder thing is setting up simulations, is more reading through ngSpice manuals and getting the syntax rather than using a GUI. So maybe there's hurdles there. But certainly, in my opinion,
the ngSpice syntax has tripped me up so many times.
Yeah, exactly. Yeah, it's not lovely. And that's also where I've been trying to use Python.
Not lovely. That's a very, very kind way to put it. I like it.
Yeah. So that's why I've also trying to be using Python to maybe abstract away some of the oddness of the Spice tool, make it a bit more idiomatic, I think is the phrase. But yeah. So.
Have you seen that Python binding for Spice? So you kind of describe your circuit with Python.
Yeah. So I think it's PySpice. Is that the one you mean?
Yeah. I think so. Yeah.
So I use that, but not the circuit description. I just use the interface. Personally, I like to see schematics, so I always build the schematics first, and then once I've got the netlist from the schematic, then I'll use Python to crunch the numbers.
Okay, so you draw the schematic, like extract it into a file that is in Spice. So that's something that Xschem can do.
Yep.
But then to run the simulations and to plot stuff, you use Python.
Yeah.
Okay, that's interesting. And we can see examples of that in your repository, I think, because I saw some Python files in there that imported matplotlib.
Yeah, so I'm slowly building up a little Python library with different convenience functions. So over time, hopefully it'll become quite useful.
Okay. And for people that are interested in kind of getting started on the analog side, could you recommend like simple projects or a tutorial, or like what should interested people do to get started?
So I think the Holy Bible when it comes to starting analog design is the Razavi books. So he's a professor at UCLA, and he's written.
So could you say the name again?
Razavi. So
Razavi.
Razavi.
Okay, I'll put a link to that in the description.
Yeah, and he has widely regarded the best instruction textbooks to analog design. So probably looking at that, they can be found on the internet, and then start designing the circuits for the best way, I'd say. Okay.
Great. Anything else you want to let us know about, or projects that you're working on that you want to share?
No, I don't think so.
Okay. Well, thanks very much, Thomas. It's been really cool talking to you. Thanks for sharing all the great work you've been doing.
Yeah.
And we'll stay tuned to see how it works out, and hopefully get you back on to tell us that you've got some successful communications with a satellite.
Yeah, fingers crossed. Thank you.
Wicked. Okay. Thanks very much for your time.
Cheers. Bye-bye.
Bye-bye.